Hi, my name is Yuriy and I'm a Maths PhD student at Imperial College London, as well as a tutor at the Elite Prep. Today I'm going to be continuing with the series where I tackle quantitative research interview problems. The problem that we're going to be tackling today is the following. Let Cn count the number of cycles in a random permutation of 1 through to 2n that are larger than n in length. Compute the limit as n tends to infinity of the expectation of Cn. So to start off with, I'm going to just introduce what a random permutation is, as well as what a cycle is. A random permutation is just a random selection of the elements which changes their order. So when we're considering these elements 1 through to 2n, the order matters. So for example, if we take the case n equals 2, so that we have 4 elements in total, then one permutation could be 1, 2, 3, 4, where they're all in consecutive order. Another example could be 3, 2, 1, 4. And another example could be 2, 1, 4, 3. So something useful is that if we have n elements, then there are n factorial permutations of these elements. And in particular, for a random permutation, we assign each permutation with equal probability. So that means that a specific permutation, sigma, will have probability of 1 over n factorial if sigma is one of the possible permutations of n elements. Okay, now that we know what a random permutation is, we should introduce a cycle. A cycle is a subgroup of the elements of a permutation which form a cyclic permutation amongst themselves. It's easier to just draw an example of that because it's much more intuitive than trying to describe it in words. So again, let's consider our example when n equals 2, so that we have 4 elements. So 1, 2, 3, 4. We'll view these as empty spaces, and we'll assign each of these empty spaces with index. So this is the first space, this is the second space, this is the third space, and this is the fourth space. Now, when we have a cycle, we have a situation where, for example, if you're in the first index, and the first index has the element 3 in it, then the 3 will point you to the third index, and then from the third index, you'll decide where to keep going. So if we in the third index then have the element 2, and in the second index we have the element 1, then this would be a 3 cycle, because the cycle takes 3 steps to return to the original element. And finally 4 is just a 1 cycle, because the index 4 points to itself. So index 1 points to index 3, index 3 points to index 2, and index 2 points to index 1. So that's a 3 cycle, as I just mentioned. And this is a 1 cycle. I'll just do one more quick example. Again, with 4 elements. 1, 2, 3, 4. If we had 2, 1, and 4, 3, then it is clear that we just have two cycles. So 1 points to 2, 2 points to 1. So that's a 2 cycle. And then 3 points to 4, and 4 points to 3. So that's again a 2 cycle. Okay. Now we can try to tackle the problem. I'll first give a hint as to what you should do to approach this problem. And then I'm gonna, as usual, go through the thorough solution. The hint for this problem is, okay. That's the hint. If you haven't tried the problem yet, you should try it now. And if you already have, then let's continue with the problem. So, solution. So we are interested in the number of cycles of a random permutation of 1 through to 2n that are larger than n in length. That naturally means that Cn is actually strictly less than 2, because we cannot have more than one cycle. If there's a cycle which is greater than n in length, then at most we have n minus 1 elements remaining, so there cannot be any more cycles with n elements or more. That means that we are only interested in the cases where Cn equals 1 and Cn equals 0. And remember that the expectation of Cn is, by definition of the expectation, equals to the sum n greater than or equal to 0 of n times the probability that Cn is equal to n. Since Cn is less than 2 with probability 1, this means that this is just equal to the probability that Cn is equal to 1. Great. The next part is to figure out all the possible cases in which Cn can equal to 1. Remember that Cn was just the number of cycles which are of length greater than n. And the way that Cn can be equal to 1 is, so if Cn equal to 1, that's equal to the union from k is equal to n plus 1 to k equals 2n of there being a cycle which has length k for any of those values between k equals n plus 1 to 2n. So this is, there exists k cycle. And note that these events are all disjoint, because if there's a k cycle, there can't be a k plus 1 cycle when k is greater than n. So that's what I discussed earlier with regards to if there's a cycle greater than n in length, then there cannot be another one. So this union is a union of disjoint sets. So that means that the probability that Cn equals 1 is equal to the probability over this union, and that, because it's a union of disjoint sets, is just equal to the sum over the probabilities. And this is exactly where the hint now comes in. So to compute the probability that there exists a k cycle, we apply some fundamental combinatorics. So for there to be a k cycle, we first need to fix k elements. So those are going to be the k elements which are part of our k cycle. To fix them, we select 2n choose k elements. Then, when you have a cycle, when you've already fixed the elements, there are k minus 1 factorial ways of permuting the elements such that we maintain the structure of a cycle. I'll explain the intuition behind this in a second. Finally, after we've dealt with all the elements which actually belong to the cycle, we want to deal with the elements which are outside of the cycle. And since we don't care about their structure at all, that means we can permute them in any way. And after getting rid of k elements, there are 2n minus k elements remaining. So there are 2n minus k factorial ways of permuting them. So we have 2n minus k factorial ways of permuting them. So this is the number of ways that there exists a k cycle. The total number of random permutations is equal to 2n factorial. because there are 2n factorial elements. So in total, the probability that there exists a K cycle is equal to 2n over 2n choose K times K minus 1 factorial times 2n minus K factorial over 2n factorial. Recalling the formula for 2n choose K being 2n factorial over K factorial 2n minus K factorial, we have that this is equal to 1 over K. Okay, now I'll quickly return to this K minus 1 factorial. So if we have K elements, right now we can assume those K elements are just labeled 1 through K. Then if we want to create a K cycle from these K elements, then the first element has K minus 1 choices, and you could have chosen any element to be first. So you have K minus 1 choices. Then the second element will have K minus 2 choices because the second element cannot be itself. So it cannot be itself. And it also cannot be the previous element because we're not yet the right length of cycle. So we basically consecutively fill in each of the indices because all of the indices will have to be filled. So it doesn't matter with which index you start. So we may as well start with the first index. So then by the time we get to the K minus 1th index, you would have filled K minus 2. So there are K minus 2 elements you can't use. You can't go back to the very first one because that would only be a cycle of K minus 1 length. So you would have to go to the Kth element. So all in all, the first element has K minus 1 choices. The second element has K minus 2 choices, and so on until the final element only has 1 choice. And that's just K minus 1 factorial. A quick example, we'll just do, for example, 3 elements. So say this is index 1, this is index 2, this is index 3. The first index, if we want a 3 cycle, can either be 2 or 3. So that's 2 choices. So we have 2 possible cycles which start with 2 or 3. Then, so this is cycle 1, this is cycle 2. If we started with 2, we would have gone to index 2. At index 2, we cannot choose index 2 because that would mean that we just don't have a cycle. We cannot choose index 1 because the cycle would only be length 2. So that means we have to choose index 3. Meanwhile, if we chose index 3, we cannot choose index 1, and therefore we have to choose index 2. And finally, because we've already had the other elements, we would have to choose index 1 in each of these. And that then becomes a 3 cycle. And we can verify that 3 minus 1 factorial is equal to 2 factorial is equal to 2. And those are the 2 cycles which we've actually found. So that's just a justification for this formula back here. Now that I've gone through this justification, we can put this back and look at calculating the probability that Cn equals 1, and therefore the expectation of Cn. So we have finally that the expectation of Cn is equal to the probability that Cn equals 1, which is equal to the sum from, so k equals n plus 1 to 2n of the probability that there exists a K cycle, but this is just equal to 1 over K. So this is equal to K equals n plus 1 to 2n of 1 over K. And now this is the second part of the hint. So we now want to use Riemann sums. So in order to do this, we notice that if we look at the function 1 over k over continuous values instead of just integers, so a sum is like looking at a Riemann sum with width 1 of just the integer values, then if we look at the function 1 over x instead, we know that 1 over x is less than or equal to 1 over x minus 1. Sorry, 1 over floor of x is less than or equal to 1 over x minus 1, and it's greater than or equal to 1 over x. The reason for this is that the floor of x is clearly less than or equal to x because we're just getting rid of the decimal part, and also it's clearly greater than or equal to x minus 1 because if you get rid of 1, that's always going to be greater than 0.99 or 0.999 or whatever decimal part we're removing. So we do this, and then this results in the opposite direction being true for the inverse. And we know that 1 over x is equal to 1 over k when x equals k belongs to the integers. And that's what we now want to use. So what we're basically doing, if we draw a graph of this, we have x and we have our function 1 over x. If we start at n plus 1, if we look at 1 over x, it's going to go something like this. If we look at 1 over x minus 1, it's going to be a little bit bigger. It's going to go something like this. And then our floor function is going to look like a staircase between them. So it's only going to go sharply down as we get to the next integer value. So that was 1 over floor of x. This one is 1 over x minus 1, and the one below is 1 over x. So that's the intuition behind it, and that's the intuition behind the Riemann sums. The Riemann sums come into play because the width that we're considering is just 1 between each of the integer values. Great. So now, because we have this result, we know that the sum of these values is also going to be sandwiched between the sum over, or the integral over 1 over x minus 1, and also the integral of 1 over x. So we have the expectation of Cn, which is equal to the sum from k equals n plus 1 to 2n of 1 over k, which is also equal to the integral from n plus 1 to 2n of the floor of x dx is less than or equal to the integral from n plus 1 to 2n. This should have been 1 over the floor of x. Less than or equal to the integral over 1 over x minus 1 dx, and it's also greater than or equal to the integral from n plus 1 to 2n of 1 over x dx. Now the convenient part is that both of these are now easily evaluatable. The left-hand side is log 2n over n plus 1, because the integral of 1 over x is log x, and log 2n minus log n plus 1 is log 2n over n plus 1. This is less than or equal to e of cn, and that's less than or equal to log of 2n minus 1 over log n, over n, because we had log 2n minus 1 minus log n from this integral. And we had here log 2n minus log n plus 1 from that integral there. And finally, because we wanted to compute the limit, we can take the limit of the left-hand side, the expectation, and the right-hand side at the same time. So we have that log of 2 is less than or equal to limit as n tends to infinity of the expectation of Cn, which is less than or equal to log of 2, which means that lim n tends to infinity of the expectation of Cn is just equal to log of 2. And that is our solution. Thank you very much for watching. I hope to see you in the next one.